So hi everyone. So in this video we will learn about ring. We have learned about groups. Now let's go one step further, and now we have a ring. So in ring what we have is uh, same as just group, we have one set. So here I am denoting the set with R. In group we had only one operator, here we have two operators. So here I am clubbing three things. One is a set, one operator and other operator. Two different operators I am clubbing with a set. This combination consists of one set are two binary operators, okay, denoted by plus R and multiply R. Okay, so this R in subscript is nothing but it is denoting that these operations are performed under this set R. Nothing else. It is just a fancy way of representing my operator. Okay. Also, note one thing, that I will explain a ring with respect to the with respect to the notations of generic with respect to our addition and multiplication symbols. Okay, but the same is true for, same rules are applicable for any other two operators also. Here for simplicity I am explaining a ring with addition and multiplication operator, but it is not necessary that they are always these addition and multiplication operator. These can be some other operators also. R is used for to denote real numbers. So I have used the notation of real number here, but it is not necessary that you for a ring it should be a real number set. Okay, so I have taken the notations of real number and addition multiplication operation, but you can apply the same concept to other set or other operators as well. So for this combination to be a ring, it should satisfy these four axioms. What is the first axiom? It says that with respect to first operator, my set R should be an abelian group with an identity element 0R. Again, it is a fancy way of representing the identity 0 subscript R. Okay. So we know that for addition, what is the identity element? That is 0 only. So I am denoting the identity of first operator, identity under first operator as 0R. Again, if it is some other operator, not instead of addition, if it has some other operator, then that will be some other identity. Okay. So, but one thing is that whatever is this R plus and identity, my combination of these two operators and my set R, it should be in that group. If I consider my set and the first operator only, if I consider these two things only, this should make an abelian group. Now you know what is abelian group, right? Let's recall what are the conditions to be a group. First of all, it should be associative. Second, it should have an identity element, right? And third, inverse of every element should exist. And also there was additional property that if the group is commutative, if the operations are commutative, then that is also called abelian group. So here we have for ring it is a must. We consider only abelian group. Non-abelian group we don't. Non-abelian group will fail the test of ring. Okay, for to be a ring, it should be abelian group with respect to first operator. We are not claiming anything for second operator yet, but with respect to first operator, it should be a group, abelian group more specifically, right? Now, with respect to second operator, it should be associative. So if I take any three elements from my set R, then this second operator should be associative on them. Okay, and you know what associative is. So it should satisfy. And now third condition is that Now second operator, under second operator we also have some identity, and that identity should not be equal to the identity of the first operator. So for addition and multiplication, we know that for multiplication identity is 1 and for addition identity is 0, and we know that they are not equal to, they are not equal, they are different. But if there were some different operator, let's say star 1 and star 2, then identity of star 1 should not be equal to identity of star 2 for it to be a ring. Okay, and here I have just defined the definition of here I have defined identity, okay, or nature of identity, because whatever you multiply with identity you get back the same element. Okay, so what are the conditions we have considered so far? It should be abelian group with first group, and it should be associative with second with respect to second operator, and the identity of both operators should not be equal. And the fourth condition is that second operator should be distributed over first operator. Okay, what do you mean by distributive? So here I am applying first operator on B and C. Instead of directly applying, if I first apply A on B, then A on C, and whatever I get I'm getting a result, then I am applying the first operator, I should get the same value. Okay, so and same thing should be true when I apply second operator from left side. So it should be distributed from right side, it should be distributed from left side. So you got what is distributive. So second operator should be distributed over first operator. So these are the four conditions which must be satisfied in order to this combination to be a ring. Okay, let's see some examples. Let us consider a set of integer. We have taken an integer. First operator is addition. Okay, our basic addition that we know, and this dot is for multiplication. Okay, so now the question is it a ring? So for ring, we have to, what are the properties? We have to check, is it an abelian group? So with respect to first operator, is it a, so z comma plus, is it a abelian group? Yes, it is an abelian group. You can check yourself. What was the criteria to be an abelian group? First condition, it should be a group. So for group, it should be associative, and we know that basic addition is associative operator. Second, it should have an identity element, and what is the identity element of plus? It is 0. Third, there should be an inverse, and how to find the inverse under plus operator? Just negate the element. So it is a group. Also addition is a commutative, a plus b is equal to b plus a. So we can say that z plus is abelian group. So it is this ring is, this combination is abelian group with respect to first operator. Now second condition is what? Multiplication should be associative. So, no, by default in basic mathematics we see that a multiplication is associative. We know that it is a known fact. So it is associative, and the identity of plus is 1 and plus is 0 and multiplication is 0. They are not equal. That also satisfied. Also multiplication is distributed over plus. So yes, it is a ring. Okay, now another example. Here we have taken real number instead of integer. So yeah, that will also be a ring. With same argument, that will also be a ring. Cool. Now one more thing, that in group we have defined the concept of commutativity. So in also ring also we will define the commutative. So in ring, the commutativity is meaningful with respect to second operation only, with respect to second operator only. Okay, so for ring to be a commutative, then with respect to second operator it should be associative. So a times a star to b equal to b star to b is to b star to a. So with respect to second operator, if I am getting commutative property, then it will be a commutative ring. Okay. Now, last but not the least, insights about ring. An element A of a ring R is called unit or an invertible element if there is an element B which belongs to R such that A times B equal to 1R. Are you getting what is this? You know what? In the axioms of ring, the only thing which is missing is that for to be a ring, it is not necessary to be it is not necessary for set R to be a group with respect to second operator. It is not necessary. It is not mandatory that this combination should be a group with respect to second operator. Okay. Why? And we know that under multiplication with respect to second operator, there can be some, if it's not multiplication, if it's some other operator, then there can be some element which are not invertible. Now what's stopping the second operator to be a group? Here we have included that with respect to second operator it should be associative. Okay, so for group we need associativity, we need identity, and we need inverse. So for on second operator, first two conditions are included here. We have the associativity of first operator, we have the multiplicative identity of that is identity of my second operator. The only thing that is missing in these four conditions is that the inverse should exist with respect to second operator for all element. That is the only thing that is missing here. Okay. So if there are, and we know that in R there will be some elements which are not invertible under second operator, and there will be some elements which are invertible with respect to second operator. So if I just consider only those elements, in R we have many elements. Some will be invertible under second operator, some will be not. So let us extract only those elements which are invertible, and those invertible elements are also called unit. We can call them unit also. So under second operator, I take all those elements which are invertible, okay, and I form a new set. So the set of units in a ring R forms a group under multiplication operation. So that will form a group. So if I just extract all the elements from my ring which are invertible under second operator, then I can definitely say that set will be a group under multiplication operation. Why? Because if it is a ring, then first two conditions are already included. What are they? Associativity and identity. These are already included in the definition, in the axioms of ring. So if I just somehow extract invertible element and just club them, just put in the one set, then I can say that whatever the set I am getting, that will form a group under second operator. Okay, and this is known as a group of units of R. Okay, that will become a group. I hope you got it.